Hi everyone, in this video I'm going to talk to you about the sources and types of atmospheric pollutions. Alright, so in this slide you can see that the majority of our outdoor air pollution actually comes from transportation. That's about 57%. And the other large percent is actually from fuel combustion, that's from not except from in vehicles, and about 12% from industrial processes, and a miscellaneous 10%. So something to think about when you're driving your car. So the two main types of air pollution are split up into primary pollutants and secondary pollutants. Primary pollutants are basically what comes out first. So you have your natural sources, like from volcanoes, and you also have man-made sources, which is the majority of your pollution, by the way. In the last graph you didn't even see volcanoes. So the majority is from man-made. But anyway, so out of the combustion from your car, from factories, you get these chemicals that come out right away, like carbon monoxide, carbon dioxide, your different nitrogen oxides, they're called NOxes, and a variety of other pollutants. And what happens, these primary pollutants get up into the air and they start reacting together. And when they react together in the air, they create new compounds, which we call our secondary pollutants. And you get a lot of your acids here, like nitric acid, sulfuric acid. You also get ozones. Okay. So your top 5 air pollutants, in terms of quantity, is your carbon monoxide, and these are for your primary pollutants, is about 48%, sulfur oxides about 16%, nitrogen oxides 16%, your volatile organic compounds, which are basically hydrocarbons, is 15%, and particulate matter, which is suspended solids and liquids in the air. That's about 5%. The other way we split up pollution is based on if it's industrial or photochemical. And in this slide you can see the industrial smog. It's also called London smog or sulfurous smog. And sulfurous smog is based on its components. The main components of this type of smog are acids. You get nitric acid, sulfuric acid, sulfurous acid, and your particulate matter. You also get carbon monoxide and carbon dioxide. And this type of fog is mainly you see on the East Coast, like New York. You also see it in London, places that aren't typically very, very sunny on a regular basis. So carbon monoxide is one of the main components of this industrial smog. And it's also known as the silent killer, since you can't smell it, feel it, whatever. You don't know it's there in the air. And if you actually look at this graph, here's the percent of carbon monoxide in the hemoglobin. There's the hemoglobin. Hemoglobin's a component of your blood, and basically the hemoglobin oxygen binds to the hemoglobin in your red blood cells, and it sends the oxygen to your tissues throughout your body, and it will then take up the carbon dioxide and release carbon dioxide later when you exhale. The problem with carbon monoxide, it actually will bind to the hemoglobin stronger than the oxygen. So it will bind stronger and longer. So if you get a lot of carbon monoxide you're breathing in, you'll actually, and at some point you could potentially have more carbon monoxide running through your blood than you do oxygen. And so what this so the more you breathe in, right, these are your parts per million, the more you breathe in, the worse your symptoms are. So for example, headache, reduced mental acuity, and this actually in studies have shown that people who are driving a lot on the freeway, especially in tunnels and traffic, actually they do get some impairment from carbon monoxide and poisoning. And then you get to the point of throbbing headache, vomiting, coma, and death. So I really recommend everybody get one of these carbon monoxide detectors in your house. It's like a smoke detector. You know, if you have, especially if you have a gas stove or you have a gas furnace, whatever, it's just a great idea. So, you know, in case something ever happens, it will ring like a fire alarm would, and you can actually get out. Sulfur dioxide was another main component of industrial fog. It actually gets converted into sulfuric and sulfurous acid, and that's been known to destroy forests. This is the Black Forest in Germany, which has a really bad problem with acid rain. It basically leaches out the nutrients in the soil and kills the trees. And sulfur dioxide has a sharp odor like of burnt matches, and it can actually form sulfuric acid in a moist tissue such as your lungs. And so this is really dangerous for especially the young and the elderly or sick people. And again, this is a major source from industrial fog, which is from burning coal. So what happens essentially is we burn coal, and coal is basically carbon with 1 to 3% impurity of sulfur. The dirtier, the cheaper the coal, the more sulfur it has. And everything we burn, as you know from the last slide, everything we burn is in oxygen and air. And when you burn coal in air with the impurities, you get sulfur dioxide. And the sulfur dioxide reacts with itself, so you get 2 sulfur dioxide, it means it's reacting with itself, in air, so you have oxygen, gives you 2 sulfur trioxide. Okay, so here's just a model of those molecules. So 2 sulfur dioxides plus the oxygen gives you 2 sulfur trioxides. One good news about this, so these, sulfur dioxides go into sulfur trioxides, become sulfuric acid, sulfurous acid, both of them, that since 1985 we have actually seen a 25% reduction in sulfur dioxide, and this is really due to public policy and restrictions on how industry burns its coal. They're required to actually use scrubbers to prevent a lot of this stuff getting into the air. So really the beginning of all of this public policy and making industry change their practices started with these killer smog episodes. And here's a picture of Donora, Pennsylvania, in the middle of at noon, in the middle of the day. It was just really, there was a lot of smog this day. And what happened, there was an inversion layer with little to no wind, so it was an anticyclonic event as well. And 20 people died during this time frame. There was so much pollution, and that the sulfur dioxide was turning into acid in people's lungs. And about a third of the residents became ill. And this was common all throughout throughout Europe and the East Coast, and this actually prompted Air Pollution Control Acts of 1955, but it did ignore the automobiles. In London, this effect had been identified since 1873. There was about 700 deaths in London. In 1911, there was 1150 deaths. In 1952, there was 4,000 deaths. And this event in 1952 led to the UK's first Clean Air Act. And in 1962, after the Clean Air Act, only 700 died. And so it was a significant drop from 4,000 to 700. Same amount of pollution essentially, but less people dying. I mean, less pollution, higher population, but less people dying. And the way they actually measured how many people died from the pollution is called an epidemiological study. So if you look at the y-axis here, this is particles and sulfur dioxide in ppm and the dates of December. And on the other y-axis, you have the deaths per day. So notice that these boxes here, these boxes on the graph, represent the particles. So there's not much particles on day 0 of December, day 1, day 2, day 3, and as we get to about day 3.5, day 4, it starts to rise, right? And peaks somewhere around day 6 and 7 and 8. And then it drops down and declines again. So these are the particles in the air, the particulate matter. You see the same trend with the sulfur dioxide, and look at the trends with the deaths. All right, the interesting thing, though, is that the deaths continue after the pollution has gone away. And this is just because the people that are ill in the hospital are still dying. So this is how they measured that death comparison to the pollution. So the other type of smog, is which you're probably more familiar with, is photochemical smog, or also called LA smog. It's a brownish orangish haze like this, and that's actually due to the NOxes. That's the nitrogen oxides in the air. And it consists mainly of secondary pollutants, ozone, particulate matter, which is a primary, nitrogen dioxide or NOxes, and volatile organic compounds. And the way basically photochemical smog works, you have an air containing a mixture of gases, from example auto exhaust, sunlight, and temperatures above 65. Sounds like California. Lots of cars, sunny, and hot. Perfect for making photochemical smog. And it helps if you have an inversion layer, right? Or if you live in a valley so you can concentrate it, like LA. So ozone is one of the main components of photochemical smog, and it has a sharp odor after, like you get after a lightning strike or around welding equipment. It's hazardous to lung function, even at low concentrations. Its symptoms include chest pain, coughing, sneezing, and lung congestion. It damages trees and crops, and so there's actually an economic loss there. So keep in mind, ozone is essential in the stratosphere, but it's bad in the troposphere. Here is just showing the progression of day, how photochemical smog is based on sunlight and heat. So you actually see differences in the pollution based on time of day. So here's at 6 a.m., right? Green means there's not a lot of ozone. But as the day progresses, 10 a.m., you start to see some ozone production. Noon, you have more ozone. And 4 p.m., it's hotter. You still have the sun out, and you have quite a bit of ozone production. So orange is even really bad. So that's Sacramento up here. And at 10 p.m., we're back down to low amounts of ozone just because the sunlight is gone and the heat is gone. So nitrogen dioxide is another component of photochemical smog. It's a brown color. That's what gives us that nice, beautiful brown smog. It has a bleach-like smell. It also produces acid, but it's not a major contribute to acid rain the way sulfur dioxide is. And nitrogen dioxide is produced from nitrogen monoxide, okay, which basically you get from burning coal or oil. So basically what happens, nitrogen is in the air. It's a natural component of our air. And so when you're burning something at a high temperature, which is your coal, your oils, your fossil fuels, you burn them at high temperatures, you have the oxygen, you have a high temperature from the heat, and so actually the nitrogen in the air starts to burn, which is kind of crazy when you think about it. We're not talking about it's the fossil fuel actually pollution from just the fossil fuel. It's the fossil fuel causing the nitrogen in the air to burn in oxygen to produce nitrogen oxide. And the nitrogen oxide is very reactive. So here you have 2 nitrogen oxides plus an oxygen gives you 2 nitrogen dioxide. And again, that nitrogen dioxide can react with water in the air and become acid, become nitric acid specifically. So the nitrogen dioxide is going to react in the sunlight. Remember, this is photochemical smog. So it's going to react in the sun to give nitrogen monoxide plus free radical oxygen. Notice that there's no O2 here, and oxygen typically is stable as a diatomic molecule. So this guy is not stable, and it's going to react rapidly with oxygen in the air. So the free radical oxygen is going to react with oxygen in the air to give you ozone, that nasty air pollution. So the other important primary pollutant that you should know about is particulate matter. So ultrafine particulate matter, and you have ultrafine, fine, and large. So fine particles is everything 10 micrometers below to about 2.5 micrometers, and ultrafine is 2.5 micrometers to everything below that, and it's 2.5 micrometers in diameter. Okay, so large particles would be like pollen, some flowers, some dust. Okay, fine particles, you're talking about paint pigments, oil smoke, some tobacco smoke, photochemical smog, insecticides. Notice that most of photochemical smog is actually under ultrafine, and you have fine here, okay? But ultrafine, and notice, look at tobacco smoke. It's very, very similar in terms of the size of the particles in the air. And why do we care about the size of particles? Why does it matter if they're large, fine, or ultrafine? Why do we care? It's all about our body. So normally in our lungs we have these hair-like features called cilia. So when you breathe in large particles, they get stuck in the cilia, you cough them out, they get into your mucus, and you get them out of your body. No problem. The problem with the fine particles, they can actually get down and get stuck. They can go past the cilia and get all the way down and get stuck in the end points of your lung called the alveoli. And this is where all your gas exchange occurs. So you breathe in oxygen, breathe out carbon dioxide. So those fine particles get stuck down there, and there's nothing to push them back out. You don't have cilia down there. So what happens, your body reacts by basically making scar tissue there, sealing off that area, and so you can't use it to breathe anymore. That's part of your lung. And the ultrafine can actually get past this region here, get into your bloodstream, right? Like you would carbon monoxide. Breathe in carbon monoxide or carbon dioxide or oxygen. All of that gets into your bloodstream. The same thing with the ultrafine. So they're finding that these ultrafine particles are getting into our bloodstream, getting into our end organs. And what does that mean? We don't quite know yet. As scientists, we don't know what that means yet, but it's probably not good getting all these ultrafine particles in our body. So this is what your respiratory toxins, particulate matter, can do. So here's a healthy tissue. Here's a healthy tissue of a 90-year-old school teacher. Here is a 40-year-old miner with fibrosis. And again, fibrosis is where the alveoli seal off the damaged area. Oops. And so this is something you see in common with coal miners, people who worked in cotton factories. You get the farmer lung, which is caused from mold. So basically anything that can get stuck in your alveoli and cause fibrosis. So it's something to think about, that particulate matter is definitely a really nasty toxin. All right. So that is the end of this section of the lecture. I will see you in our final lecture on basically public policy and how to control these nasty toxins in our air. Bye.